So holography, in short, would be the idea that we might be an hologram. It's at the same time a totally radical and a totally conservative idea. It's conservative because it says, look, all we need is quantum mechanics. All we need is quantum field theory. Gravity then comes along for the ride. Gravity is emergent.
What is holography, and how can it help us understand quantum gravity? That's what this conversation is about. I speak with theoretical physicist Pedro Vieira, one of the world's leading experts on holographic dualities. We discuss what quantum gravity is, why it's so challenging to solve, and explore the fascinating idea that our universe, including gravity, might be a special kind of hologram projected from a lower dimensional quantum theory. This is the Escape Sapiens podcast. If you enjoy it, the best way to support it is by subscribing. And now, here's Pedro Vieira. I hope you enjoy.
Escape Sapiens.
Let me start with the hardest, biggest question in physics. What do physicists mean when they say they want to quantize gravity, and why is it difficult?
Okay, so first let me maybe mention a little bit about what is quantum mechanics, and then I can tell you what would it mean to quantize gravity. So our intuition about physics would be that particles follow specific trajectories in space-time that I could tell very, very, very precisely. So if I drop my pen will just fall, and it will follow one trajectory, very precise, and I can predict exactly where it will land if I know exactly the initial velocity and position. It turns out that the world does not work like that. It turns out that the world works in a completely different way, where particles, they do not follow one trajectory from point A to point B. And it turns out that we cannot know exactly what's going to happen. It turns out that the rules of the world are governed by so-called quantum mechanics, which tells you that particles go from one point to another, basically following all possible trajectories. And then, as if it was not crazy enough, we can only compute what's the probability of this or that happening. What's the probability of particle going from A to B versus from A to C, A to D, etc., etc. And this is really something mind-blowing. It looks insane. It looks like I'm starting this conversation right off the bat with something that doesn't make any sense. I mean, how could it be? That's not what we see. And indeed, there are some things in physics that look like taken out of science fiction, and it is just how the world works. And it turns out that those quantum effects, however, we don't see them on our day-to-day because they become important, they become really significant at very small distance. And then at very short distances, if we were very, very small animals, we would see these very crazy quantum effects. But big as we are, we don't see them anymore. They fade away, and things behave classically. And so matter behaves classically, and then we quantize it. And by quantizing it, I mean we understand how it really behaves. We understand that it's really not how we thought. And why do we care about quantizing matter and about understanding things quantum mechanically rather than classically? First of all, forgetting about gravity, but just matter, usually electrons, protons, and so on. Why do I care? Because that is, for example, what describes all of chemistry. If we didn't understand how particles really work, we would still be confused. Why do we exist? We would still be wondering, why doesn't the electron rotate and starts losing energy and falls into the proton? And why doesn't everything fall into the proton and we just disappear? Why do we exist at all? And so it's not like a small luxury. Let's try to understand quantum mechanics. We would understand nothing. We will not understand why we exist. We will not understand the universe at all. Now, that is an extreme case where to even understand the basics of chemistry or of electricity, we need to understand quantum mechanics, and we need to understand that the behavior of very small particles is really different from the classical behavior. And this transition from classical to quantum, we call it quantization. We say we have a classical system, and then we quantized it, and it became quantum. So Another way of saying is that quantizing is understanding how things really are. We think things are classical, but that's just an approximation. Things are really quantum. So understanding how to quantize gravity is understanding what are really the rules of the universe. We have gravity, we have black holes, things fall, we fall, gravity exists, there's no denying that. And we want to understand what are the rules of the game of the universe. How does the universe behave? Now, we can survive relatively well without knowing the answer to this question, contrary to the first one I said. Understanding quantum mechanics was crucial. We would not understand chemistry. We would not understand why we are here. So quantum mechanics, it was really screaming at us that there are paradoxes and puzzles about how the universe works that we need to understand quantum mechanics. Quantum gravity, these effects where quantum mechanics and gravity would be important at the same time would show up at very small distances. And gravity is only important when things are heavy, right? If you have something that's not heavy, gravity is not so important, right? Two pens, they both have mass, but they don't attract each other gravitationally significantly. They don't start moving in your table one towards the other because of gravity. Gravity is very weak. So for gravity to be important, things need to be very heavy. For quantum mechanics to be important, things to be very small. And therefore, quantum gravity is the theory that will describe gravity and quantum mechanics at the same time, but it will only show itself with very significant effects when things are very heavy and very small, such as at the singularities of black holes or at the beginning of the universe, at very, very extreme cases. And just because of that, it's very hard to tell what's going on. We cannot do experiments. We cannot jump inside black holes and see what's happening inside a black hole. We cannot go to the beginning of the universe to look at it and see how it is. So it's hard. It's hard because the conditions where we would see the rules of the universe, where quantum mechanics and gravity need to be important at the same time, are very, very extreme. And it's not like we have experiments that we can do at such extreme situations. Now, with quantum mechanics and chemistry, you could derive all the theory of quantum mechanics, meditate about it, develop all the theory, and eventually, much later, predict chemistry and so on. And then people would test and do chemistry experiments and be happy, even if they did not have powerful electron microscopes to see the orbitals of the atoms and so on. They would be happy enough with the consequences of quantum mechanics. So there is some hope that we might eventually find some consequences of theories of quantum gravity that we might test. But it's hard. I mean, it's ideally, we would find an experiment. We would get some signals from the Big Bang. We would have some predictions about black holes that we could go about and testing. But yeah, it's hard because it would require very extreme situations to for these effects to be significant.
But then, how do we know that we need to quantize gravity? Or let me ask the question a little bit differently. You researched quantum gravity, but you could have gone into condensed matter or into cosmology or any other area of physics or research for that matter. Why did you go into quantum gravity? Why did you think this was an area where you could make progress and that was meaningful?
There are many different axes inside physics. There is theoretical, experimental, there is studying small stuff, studying big stuff, there is working in big collaborations of many scientists and working alone. There are many different components. And one axis that you could imagine in research in physics is problem solving. There are some people that really like trying to find hard problems and trying to solve these hard problems. There are people that are more seeking conceptual ideas and trying to understand what could be, trying to relate big pictures of different neighboring fields or trying to understand concepts in a more phenomenological way or something. When I moved into physics, I was more of a problem-solving kind of a person. I really wanted the challenge of understanding there are some theories that we don't know how it works. We have some hints, but there are some puzzles that we would like to understand. They don't just apply to quantum gravity. Quantum gravity is an example of something we don't know how to solve. But I would say that quantum gravity becomes hard in regimes where quantum mechanics is very important. we could say that a lot is going on. So when there are not that many quantum effects, things are easy. But when there are a lot of quantum effects, things are hard. And that doesn't apply just to quantizing gravity. It applies to condensed matter, like you said. If you have a system where all particles are interacting a lot with all particles, generating some very complicated coherent behavior, that's very challenging as a problem. What is the mathematics that I use when I have so many quantum effects? It's not like I can look at one, look at another, look at another. I need to look at all of them at the same time. And so developing, how do we think of physics? How do we develop the necessary mathematics to study systems where quantum effects are really very big? Is basically the common thread of everything I've done so far. It's about trying to understand how to tame quantum mechanics when quantum mechanics is really wild. And quantum gravity is one aspect of it, but just understanding general quantum mechanical theories, general theories of nature, when the quantum effects are very strong, is something I'm very interested in. I don't discriminate against or in favor of quantum gravity.
But then how do you know, so a much more basic question then is, how do you know what a good question is in physics? So to give you some context, you know, there were researchers in the past who tried to derive the distance of the planets from the sun, right? Mm-hmm. And there are lots of questions that you could ask. For example, why do we see 3 particle generations? You know, why do we see the mass spectrum that we see? How do you know, is there some rule of thumb that you use to say, you know, this is really a question that I can solve, that should have a solution that really does have something fundamental underlying it, as opposed to, you know, this is the distance measurements of the planets from the sun, which I shouldn't be able to derive from first principles?
Good. Yeah, so that's an excellent question about how do we choose the questions, the problems we work on, right, in physics. And I think that's a very important challenge, which is to try to be as crazy as possible while being reasonable. You don't want, it would be much easier to just do what you know how to do, right? There are many things that in general, if the problem is computational, I'm quite good at it. So I could just be solving computational problems and so on. That would be relatively easy to do. On the other hand, if all I do is think about speculative questions about black holes, what happens when Alice falls in the black hole and she's holding hands with Bob and they throw signals of each other and so on, then I'm just blah, blah. I mean, it's just mumbling things and I can't really make sense of anything I'm saying, and it's too wild for me. So I need to find the balance. I need to find what's a question that's crazy enough that it's exciting and interesting, but well posed enough that I can try to address it. And finding these questions often involves discussing with people over lunch. Often involves saying, could this be true? Could it be that sometimes when quantum effects become very, very strong, they simplify again because of this or that principle? And you should try in your brain to be capable of accepting some wrong ideas or ideas that you think this is probably wrong, but let me try to go with it for a little bit to try to explore it, because maybe I find something right in the neighborhood of it. But at the same time, you need to be very conservative with everything else, because physics is very rigid. You cannot just change things and try to create different rules. Everything would break down. I mean, it's very easy to go into some rabbit hole where you start coming up with lots of crazy ideas. You can have one crazy idea. You cannot have 5 crazy ideas. So it's fine to have one crazy idea with lots of very conservative ideas around it, and then you explore. And then next morning you wake up and you kill that idea and you turn to another crazy idea, replacing the other ones by very conservative hypotheses. And this tension between being highly conservative, because most things in physics are working, I cannot just change things. I mean, we have experiments that compute things and we predict things, and then people go and measure and there are like 30 digits of agreement, right? I mean, it's only in physics that we have this luxury, that we can compute something and tell, look, you are going to measure this magnetic moment and you are going to get 2.0567, and you are on the phone and 30 digits later you are done. And then the person goes and measures and indeed 30 digits are correct. It's not like we say it's 2 plus minus 1. It's really impressive. So I cannot just start changing how things work and seeing, I mean, it will destroy everything. But on the other hand, then we have big questions about the universe that we don't understand. What's the origin of time and how did the universe begin? So we have this tension that there are some big things we want to understand. Why are we here? Why did the universe begin? What was at the beginning of the universe? And at the same time, we have a structure that works very well that we can barely touch. Otherwise, everything breaks. And so it's fascinating. And I think, so searching for the questions, it's very much a group effort at many levels. It's the talks you give. At the end of the talks, you say, maybe this would be interesting, and you wait for feedback. It's the conversations at lunch with your colleagues, where you bounce ideas. It's the discussion in the blackboards with students, where you try to brainstorm and say, could this make sense or not? And I think that part is very much a group effort, small groups, but a group effort. And then digging deeper can be can be done either in group or by oneself. But I didn't really answer. What makes a good question? It's subjective. Not everything in science is really objective. People think physics is super, super objective, but when you are searching for truth, not everything is connected. It's not like you say, oh, this is true, and this is true, and this is true, and this is true. Sometimes you need to give jumps. You need to, let me try to assume something crazy. Now I'm in the wilderness, right? Now it's probably wrong. It's a dark place where I am. And when I say where I am, it's because I have in mind thought experiments. It's something we do in physics all the time, is we go to imaginary worlds where we change the number of particles, like you were saying. Why do we have a given number of particles in the universe and not something else? Well, in my office, I have how many particles as I want. I change the rules of the game, right? I decide, today I don't have 3 families, like Shane was saying, I have 1 million. What would happen? No one stopped me. And but I will have one. I will have that as a crazy idea, and I will try to maintain everything else. And maybe I will reach a contradiction. Maybe I will see, oh, that would lead to a contradiction, and then I would answer the question why something is like it is.
I want to eventually, so just to give you some idea for the trajectory of the conversation, I want to get onto some of these crazy ideas. I want to ask you about the bootstrap and asymmetric theory and all sorts of stuff, holography. But before that, I want to ask a question that traditionally or famously has not translated very well on podcasts. So I'm going to throw this at you and hopefully it sticks well. But one of the most beautiful ideas in physics is gauge theory. Again, for someone with no background in physics, what is gauge theory and what do symmetries have to do with forces?
Let me describe. So some theories of nature have this property of gauge symmetry. And there are many. And one of them that has quite a bit of this gauge, people call it symmetry, but I'm going to tell you in a few seconds why I think that's a bad name, is gravity. So let's imagine that we are in a universe. And one of the fundamental things in that universe is to understand what are the various points in space and time. So you could imagine a wall, and you want to mark the points on the wall. Later, you are going to tell your friend, please put some picture on point number 27. So you go to your wall with a pencil and you start putting points like 1, 2, 3, 4, 5, 6, 7, and you mark your wall full of points there on the wall. And then you go and tell someone, please put some painting on point number 27. Now, someone else could have gone there and labeled points completely differently, maybe A, B, C, D, E, F, and so on, the points on the wall. Maybe instead of the points being spaced by 1 centimeter, now they are spaced by 1 inch. Maybe they are not even spaced uniformly, who cares, provided there are enough points. And so these are all different ways of labeling the points on the wall that then someone can go and attach a painting to. Does it matter? Is one labeling better than the other? No. It's all the same. There is some freedom. You can use some labeling of points in the wall or of points in space-time. I can use another labeling. Each person can use another labeling. you should probably call it some gauge freedom, in the sense of you have the freedom of choosing different ways of labeling points. And it doesn't matter. That's not physical. Now, what's physical, of course, and what's meaningful is if you tell the person, put a painting on point 27 and 28 and 29 and 30. Wow, that's a lot of paintings that are close to each other. It's very cluttered there. That's physical. You could measure now distance between paintings and see what it is. But the labels of space-time, understanding where are the various labels, what is the point 1, what's the point 2, what's the point 3, that's some freedom that you have. And so your theory of space-time, for example, which is a theory that where the arena where things move is this space-time, it's space and time, so you have points not only in space but in time as well. The way we describe these points must come in a mathematically very, I won't say rigid, but at the same fluid way, that it must allow for some people to choose some description of points. Someone else should describe points totally different. And the mathematics should be such that these two very, very different descriptions should be describing the same thing. And it's remarkable that we can do it. It's beautiful that we can do it, that we have mathematics that describe things with coordinates, which are this marking of points, where do we put them? And I use some coordinates, and you use some other coordinates, and someone else uses other coordinates. And now you would say, oh my God, it's a disaster. I mean, how are we ever going to agree? How are we ever going to be able to compare things? And the beauty of it is that we can. All these different choices of coordinates, they are what we call different, they are all related by different gauge symmetries. This is what, and they would describe exactly the same thing. And so, now, I use the word symmetry, but you are probably thinking, well, there's no symmetry in what you said. There was just a wall. The wall might be very symmetric, but it might also be a messy wall, and there were points on the wall. It was not really about symmetry. It was more about redundancy, about understanding that there would be different ways of describing space-time, and they should all be equivalent. And you would be right. People call it gauge symmetry, and in short, they are just wrong.
But the redundancy is sort of related to symmetry, right? If I have a ball, I can rotate that ball and it sort of looks the same from every direction. And we say it's got some rotational symmetry or some redundancy in the description of the ball, right? So they are related in some sense.
No, a ball really has symmetry. It's like a beautiful shape. A ball, I rotate the ball and it's the same ball. Now on that ball, let's mark the points. Let's put the points 1, 2, 3, 4, 5, 6. There are infinitely many ways to putting points on the ball. I can label them uniformly spaced. You can choose a different way of putting the points. Someone else chooses a different way. There are infinitely many ways. So if you want the coordinates on the ball, it's like an infinite space of choices. The symmetries of the ball, it's beautiful. It's very symmetrical, but it's not infinite. You can rotate it like this. You can rotate it vertically, horizontally. There are like 3 ways of rotating the ball. It's very different. Symmetries of the ball, there are 3 symmetries if you want. Gauge redundancies of describing points on the ball, there are infinitely many. So it's a big difference. It's from 3 to infinite. So theories that describe geometries living on the ball, if the ball was a universe and you would have insects living on the surface of that ball, the quantum gravity that would describe those observables living on the surface of that ball would need to have that redundancy of description, that someone picks some coordinates, someone else picks a different labeling of points, they must agree. On top of that, because the ball is very symmetrical, there would be things that they would observe that would be physical, namely all points are the same, for example. There would be no one special in that universe. Everyone is the same, right? Because the ball is the ball. Everyone is related by a symmetry to everyone else. So there is no center of the ball. There is no, so that's physical. That's like saying that space is very special. It's a space where all points are equally good. So that's a very powerful statement that is independent of how you decide to label points. So symmetry, it has physical consequences. Gauge redundancy, it's a mathematical statement that I have freedom in how I describe something.
So then let me ask, so I had a second part to the question. which was how do symmetries relate to forces? And then to give you some context for this question, I'm then going to ask you, is gravity a force?
Yeah, that's a tough question. I'm afraid if I say something very general about that question, I'll say something wrong. So let me think what I want to say. So let me say, so you ask if gravity is a force.
Mm-hmm.
Maybe I can start with that, and then you can ask again the beginning. So in nature, we can divide particles, the fundamental particles, in basically two groups: the heavy ones and the light ones. So the light ones would be the particles that have zero mass. They are just energy. Particles of light, the photons that propagate electromagnetic waves, have zero mass. Particles of gravity that propagate gravity and that are exchanged between the moon and the earth to maintain the attraction between the moon and the earth, they are called gravitons. They also have zero mass. The particles inside the nucleus that maintain the constituents of the proton together, they are called gluons. They are also massless. Everyone else is massive. The electron is massive, the quarks are massive, everyone else has some mass. Some are very heavy, some are very light, but they all have mass. So the massless ones are basically the ones I said, unless I forgot some. Now, and how do particles work? Particles work by approaching each other and then bouncing particles at each other. So you can imagine that you have like two electrons moving, and as they approach each other, they throw a photon at each other. And because of the recoil effect, as you are running and you throw something, you deflect, right? So you are running, you throw something to the side, and you deflect a little bit to conserve your momentum. And so these electrons that are moving and throwing photons at each other, because of this throwing of photons, they recoil and their trajectories is modified. And that's how electrons interact with each other. Now you could ask, do they also throw at each other massive particles? Yes, they do. But that's not very important to describe the forces, because when you throw a massive particle, the range where the particle can reach is very small, and in practice, that's irrelevant. So in practice, it's like you are throwing balls at each other. But if you throw a big table at someone, the table will fall next to you and it will have zero effect on the other person, right? You need to throw a small ball to be able to hit someone else. And so particles are moving and they are throwing stuff at each other, but in practice, it's the massless stuff that matters. Mm-hmm. And the massless stuff that you throw are photons, and then you have electromagnetic force, or it could be gravitons, and then you have the gravitational force. Now, what happens, a big difference between these two is that we can measure in a lab photons, but we never measure the gravitons. So photons, our technology is good enough to measure photons. We can measure individual photons. In fact, not even technology. Our eyes can almost capture individual photons. We can capture maybe like 9 photons. It's enough to trigger our eye. We are almost good enough. But gravitons is much harder. But we know they exist, or more or less everyone believes they exist. And we can measure gravitons when there are many, many, many of them. And we can measure the effect of gravitons. We say, let's assume there are gravitons. Let's assume they are being exchanged, thrown at each other. Everyone that has mass throws gravitons at someone else. And so the moon has lots of mass, so it's throwing lots of gravitons at us. We have lots of mass. We are throwing lots of gravitons at the moon. And then we do the computation. What would the effect of that be? And the effect is exactly Newton's law, and it will tell us exactly the period by which the moon should rotate around us and so on. So it matches perfectly our intuition. Now, sometimes in physics, we can describe the same thing in 2 different ways. I just described how the interactions work between the Earth and the moon. But there is a totally different way of describing the same thing that people probably heard, at least in some popularization books, or read in popularization books or documentaries, which is the idea that planets and heavy objects deform space-time. We were discussing before space-time, the sphere or maybe the wall, and now you could imagine a space-time that's curved by the presence of heavy objects. And the Earth curves the space-time in a way that the moon is going straight, but the space is curved. And so the moon is kind of falling towards the Earth in this curved space and effectively rotates around the Earth. Who is right? Is the Earth throwing gravitons at the moon, or is the Earth deforming space-time and the moon is propagating in the deformed space-time? And the answer is both are right. It's are two equivalent descriptions of the same thing. It would be like saying, is water a bunch of water molecules or is it a fluid? Well, it doesn't matter, the same, whatever you want. If you prefer to do computations with molecules, you do computations with molecules. If you like working with fluid equations, you work with fluid equations. If you have lots of molecules, you cannot tell the difference. It's basically the same thing. However, if you have very little, if you have a very small number of molecules, or if you zoom in close to the water and start seeing molecules evaporating, then the molecule description would be better. That would be a little bit more correct. As soon as you zoom out and see things from the distance, it doesn't matter. With gravity, it's the same thing. Whether we describe it with a gazillion number of particles being exchanged, or with a collective effect of those many particles, that there are so many that effectively they generate some smooth wave or some smooth force like it does, you cannot tell the difference. You would need some very, very high energy experiment to tell the difference. And so, is gravity a force, or is it a deformation of the space-time and particles propagate in straight lines in that space-time, but the space-time is curved and therefore they form closed lines? It's the same thing. It's just it's a matter of taste, which one you want to adopt.
So then the harder question is, what do forces have to do with symmetries? Is it just that, you know, you describe this picture where particles throw particles at each other, let's say call them bosons, in order to interact with one another. And it could be that the description of that throwing or that interaction has some redundancy in it. That could be the link. But do you have a clear picture?
The particles that we know in nature that have zero mass and that propagate very far turn out to be described by systems that mathematically have this gauge redundancy. They are gravity, electromagnetism, gauge theories. They have this redundancy of their description. I might be wrong, but I could imagine a scenario where I also have massless particles that are not. They could exist, other massless particles that are not necessarily related to theories that have this redundancy. They are not realized in nature. Somehow in nature, all these massless particles, they are related to theories that have this extra gauge symmetry.
Let's jump onto a topic that I know you do have a background in, and which is, I mean, this is a stepping stone into your actual research. So again, for the listener who, I apologize, I keep saying, for the listener who doesn't have a background, what is quantum field theory? And the follow-up question is, why does it do a good job of describing particle physics, but not gravity necessarily?
So like I said before, quantum mechanics, one of the most fundamental principles of quantum mechanics is that when you look at a particle, the particle follows all possible trajectories it could follow. It doesn't go through one trajectory. It goes through many, many trajectories. What if we don't want to study one particle, but many particles? What would be the theory that now has not one particle going through many trajectories, but many particles going through many trajectories? And that's quantum field theory. So quantum field theory, if you want, is just the conceptual step between going from situations where I care about one particle and one particle only to the situations where I care about any number of particles. And there is one scenario where quantum field theory is very important, which is when we describe what is called relativistic quantum field theory. The relativistic comes from combining quantum mechanics with the theory of relativity of Einstein. And that scenario is when we are dealing with big energies, because we know that energy is mass. And so if we send two particles at each other with huge energy, like we do in particle accelerators, like at CERN, we send the particles against each other and they collide, they make this explosion, and out of this explosion, could come out 10 particles. So 2 came in and 10 came out. The number of particles is not something that is conserved. That's very counterintuitive, right? We imagine I have a particle, it's a small ball, and I look to the left, I look back at the particle, and it's still 1. It doesn't change, we would imagine. But that's wrong. In nature, the number of particles is not something constant. It changes. You send 2 at very high energy against each other, maybe you get 6, maybe you get 8, maybe you get 10. The number of particles changes. And that doesn't work in quantum mechanics. That needs quantum field theory. So quantum field theory, you have many, many particles. They are all going in crazy trajectories. They all follow all possible trajectories, and that's how the world works. And moreover, they collide with each other, and 2 particles produce 4 particles or more, and their number is changing. And so you should imagine this gas of particles all moving and interacting with each other, sometimes disappearing the number of particles, sometimes increasing the number of particles. And the mathematical framework that describes all these particles is called quantum field theory. Field comes from the idea that these particles, I'm describing them as points, and I said I have in my mind many, many, many points spread out through the universe. But the more modern way of thinking of particles is a bit like I have some field, some permeating field, like some tide, like I'm looking at the ocean. And then there are some small waves, some small excitations of this field, and those are the particles. And that turns out to be a correct way of thinking of particles. They are excitations of a field. And so quantum field theory describes this field, like the surface of the ocean, like I said. And we are looking at the surface and we see a wave here, a wave there, a wave somewhere else, and then maybe 2 waves collide and produce 4 waves. And this description of this fluid, this field that creates particles and these many, many particles interacting with each other is what is quantum field theory. And now you could imagine that quantum field theory is more or less quantum mechanics if I have very few particles, if I have 2 or 3 particles. And if they are far away from each other, then they don't start annihilating and so on, then things are relatively easy. And things become hard when I have many, many particles and when they are all crammed in a very small space and they are all eating each other and a lot is going on and so on. And that is by definition what must happen for quantum gravity to have quantum strong effects. Because we said quantum gravity only matters when things are very, very heavy. But things are very, very heavy if there are lots of particles. So by definition, I have lots of particles there in a very, very small space, and they are all interacting, and there's a lot going on. And when there's a lot going on, you are doing a very complicated computation. You cannot just keep one term of an equation or another term. You have many, many terms going on. It's not special to quantum gravity. It's special to anything where many particles, where the behavior of many particles is important. It happens in other situations. When water boils, for example, the behavior of many, many particles is important. It's not just 1 or 2 particles. Many, many particles play a role. And so studying the transition between liquid and vapor in water, for example, is also very hard.
What is holography? And why should we care about holographic dualities?
So holography, in short, would be the idea that we might be an hologram. So this is kind of a bit of a provocative, very short answer. But the idea could be that it reminds a little bit about this simulation theories that we might be in the Matrix or something like that. It's not so different, actually. So we could imagine an hologram. An hologram is like a 3-dimensional projection, like in Star Wars, that you have Princess Leia, right? And she's talking there. And you could imagine an hologram of a bird that is flying, and the bird is flapping his wings to fly, because otherwise the bird will fall. But if that was an hologram, that is just an illusion. Inside the computer that generates the hologram, gravity is irrelevant. Who cares about gravity, right? The bird in the 3-dimensional being generated is not there. It's just an illusion. The hologram was created by the computer. The bird flapping the wings, the gravity that pushes the bird down, is an illusion. There's no gravity in the computer that generated the bird. So this holographic idea, it's a very crazy idea. It's the idea that perhaps space and even gravity is an illusion. Not everything is an illusion. Quantum mechanics is not an illusion, for example. But gravity and space could be. Perhaps the bird doesn't exist. Perhaps the bird is a projection of an hologram into, and it's projected out of a computer. The computer, inside the computer, you have the usual rules of quantum mechanics, but there's no gravity. You don't need gravity. It's a very light computer, if you will. And the computer is two-dimensional, and the bird is in 3 dimensions. So the number of dimensions of the computer, it's less than the dimensions where the bird seems to be. And that's why it's called an hologram. Now, a question could be, could we be an hologram? Could we think that we exist and that we are 3-dimensional beings? Could we be generated, if you want, by an hologram and be an illusion? And could it be that gravity, that we think is something very real, could it also be an illusion? Okay, so now this is basically the working premise of this holographic dualities, and it looks insane, said like this. Why would we suddenly start saying that, no, we don't exist in 3 dimensions, we are a projection of a lower dimensional thing? Where would such ideas come from? And they came from thought experiments thinking about black holes. Okay, so let me say 2 things. One is that there is a chain of logic, if you want I can describe it, that leads to the idea that perhaps we are an hologram. And that's a sequence of thought experiments that and I can also say what a thought experiment is. So that's one thing. And then a few years later, there was a concrete proposal that said, look, here is a theory. It's not a theory that describes our universe, but it's a well-defined theory. And in this theory, this kind of hand-waving ideas that maybe we are an hologram, maybe the bird is not real, blah, blah, blah. These crazy sounding ideas, they are mathematically precise, and there are equations that come with it, right? So there are these 2 things. It sounds crazy, I agree. But one, there is a theory where it's precise. So that means that perhaps it's not so crazy. Whether our universe is an hologram or not, I don't know. If I had to bet, I think probably yes, but I'm not sure. And then there is the logic of where did this idea originally came from? Why would we ever start saying things like that? And but we do say things like that. So maybe if you want, I can tell you a little bit about these ideas related to black holes that lead to this idea that perhaps things are holographic.
Yeah,
or if you have another question.
No,
okay.
Take me through it. Yeah.
The basic idea goes as follows, that if you have a physical system, it has a given amount of information inside it. So to describe some system, we describe the information that is in it. Like we were discussing before, we have some paintings in the wall in position 27, 28, 29. So that was the description of what was going on inside. And if you had many more paintings in many more points, you would have more information inside the room. And that amount of information, that amount of stuff inside the room also goes by the name of entropy or disorder. And it's something that always increases. When I let things evolve, the mass, the complexity always increases. There is the famous picture that if I have a glass and I drop it, the glass scatters, right? It breaks into small pieces and now it's a mess. And before it was trivial to describe the glass. I would just say the glass is in the corner of the table. And then after it falls, it's a mess to not only to clean it, but to describe it. I have to say there is a piece in the corner of the room, there is a piece below the sofa, there is a piece in my foot. I mean, it takes forever. So the information, the amount of information grows. It always grows. So that's a physical principle. It goes by the name of the second law of thermodynamics. Okay. So now starts the thought experiment. I'm here in my office and I start putting stuff inside my office. And as I do it, it's becoming messier and messier. Okay, so the amount of stuff, the amount of information is increasing. And I keep opening my door and inviting people in, and it's more and messier and messier. Lots of stuff comes in, the mass is increasing, the entropy is increasing, and eventually the office is so packed, it's so full, that it becomes so heavy that it forms a black hole. So isn't it amazing? I can imagine such things. It's fantastic. So now my office became a black hole. And in the process, it was becoming messier and messier and messier and messier. And now it's a black hole. It's just a sphere, just a black sphere. It formed this very heavy object that nothing can escape. So this leads to the conclusion that the black holes, if you want, are the messiest objects there is, because the mass was always increasing, and eventually it formed the black hole. Okay. Now it turns out that in physics, we can compute entropy of stuff. Right? We can compute entropy is basically how many ways we have to describe a system. It also can be described by how when you interact with a system, you can tell if it's messy or not. In the same way that we enter a room and we can tell if it's messy or not. And when we compute the entropy, the mass inside the black hole, we find something really surprising, which is that if the black hole has a given size and you double the volume of the black hole, the amount of mass inside does not double. Instead, if you grow the black hole, the mass inside is not proportional to the volume inside. It's proportional to the area of the black hole. That's very surprising, right? If you look at the building and you would say like a museum, and you say inside that building, there is some units of mass. Okay, I could tell what there are 77 units of mass. And now I double all length scales so that the volume of the museum is multiplied by 8, 2 times 2 times 2. And you would say, well, if before there was some mass, now that the museum has 8 times more volume, there could be 8 times more mass inside. But no, I will tell you no, there's only 4 times more. It's only proportional to the area of the museum. You increase the museum and the mass is proportional to the area of the museum. Well, what would you conclude? You would conclude, well, it must be that this is one of these modern art museums, very empty, where things are only on the walls. Because if things are only on the walls, indeed, when the surface of the wall doubles, the mass doubles. So maybe it's not about the volume, it's about the surface. So it looks like if we believe this conclusion, then I'm saying I'm putting stuff, more and more and more stuff inside my office till it forms a black hole. And when it forms a black hole, the surface of the black hole is enough to describe what's inside. But that was the maximum of information. So before, it better also be enough. If at the maximum it's enough, before the maximum, it should still be enough. And so we are led to the conclusion that perhaps to describe some region, it's enough to describe the surface of the region. But that's what an hologram is. An hologram is a two-dimensional surface that emits three-dimensional information inside. Well, so then this leads to the idea. So maybe gravity is holographic. Maybe there is a way of describing gravity with some kind of very thin quantum computer in some big imaginary sphere. And that computer will describe everything that is inside. So this is the so-called holographic principle or holographic idea. And then you see, you can have an idea like this in physics, but unless you write an equation for it, it's just some wishful dream. You see, I had a thought experiment, but maybe there was a mistake in one of the steps of the thought experiment, right? I mean, I tried to describe it in a way that you agreed, hopefully, with every step, but maybe there was one step that was not totally watertight. So at the end of the day, I need an equation. And that was what Juan Maldacena in 1997 wrote. He said, look, I don't know about our universe. I don't know what is the quantum computer that will describe our universe. But here is a very symmetric theory that is not so different from our universe. It also has these massless particles. It also has this gauge redundancy that we discussed. It has particles. It has different types of particles. Some are bosons, some are fermions. We could describe what these are. And in this theory, at least, we have two ways of describing it. We have a theory of quantum gravity with black holes and all the mysteries of quantum gravity. And we have a quantum computer with one less dimension. And they are the same. They describe the same thing. So whether you think of the theory with gravity or without gravity, it's the same. From that point of view, you could say gravity is emergent. Gravity is holographic. Gravity is an illusion. A bit like when we were describing before, what about the fluid of water? Is it molecules or is it fluid? And we said, whatever you want. But then I also said, but the most correct one is the molecules. The molecules is always right. The fluid is only right when you look from far away. Same thing here. For most experiments, you would see a black hole and you would see particles moving around planets and so on, and that would be good enough. But if you ask very, very, very tough questions, very microscopic ones, you better use the quantum computer to get the answer. And the quantum computer description, this holographic description, would be the most accurate one.
And so when it comes to linking the holographic idea to quantum gravity, is the usefulness that it's easier to do computation in the lower dimensional theory, and so you can go ahead, you can compute everything that you want, and then you have a map back to the three-dimensional hologram, let's say, where you now have a good, rigorous description of quantum gravity through this duality. Is that the basic idea?
If the world is holographic and if it works like we were saying, like gravity is emergent and it all comes from a quantum computer, the good news is that we understand quantum computers. The good news is that conceptually, quantum computers are governed by quantum field theory. Quantum field theory can be easy or hard. Sometimes it's easy, sometimes it's hard. Whether it's useful or not, it's a different question. You ask, is it going to be a piece of cake to do computations in the quantum computer and understand mysteries of black holes and so on? No, it's going to be hard. But the rules of the game are given. It's like it's electronics, if you want. It's you have a bunch of quantum mechanics in the boundary theory, and it's the usual rules of quantum mechanics that we learn in university. So in a way, it's at the same time a totally radical and a totally conservative idea. It's conservative because it says, look, all we need is quantum mechanics. All we need is quantum field theory. Gravity then comes along for the ride. Gravity is emergent. That's very different from what you could be trying to do. You could imagine, I'm trying to understand gravity, and gravity really exists, and I'm going to try to think of gravity as built of small building blocks and so on. And in this picture, that's not the way to go. In the same way that the fluid, the way to go is to go from fluid to molecules and not from fluids to atoms of fluid, right? Or to some small cubes of fluid. That's not the proper quantum description of a fluid. So we went from a fluid, which was something beautiful, continuous, full of velocities, where we can swim and so on. We went back to molecules, small dots, small particles, and so on. In a way, it's also conservative. It's like, again, only particles exist, only quantum mechanics exist. Fluid is an illusion. So you could say, we could try, why don't we quantize fluids? And so on. And we'd say, oh, no, that's not really the right way to think about it. You should really think fluids are a collective behavior of many particles, and particles, we understand how to do them quantum mechanically. So when we ask, should we quantize space-time? Should we try to understand space-time as something quantum and so on? Maybe, but maybe not. Maybe space-time is a bit like the fluid, and we have to understand, and the atoms, the molecules that make the fluid, the analog would be this hologram, this quantum computer. That's a possibility. It could also be the case.
One of the interesting questions about black holes is what is the meaning of the singularity at the center, right? Is there some way of resolving it? And there are other singularities, like at the beginning of the universe, right? And so the question I have here is, if we have this duality, we have this description, the quantum computer, let's say, on the one side, and then this hologram on the other, where we're experiencing black holes and the universe around us. Is the description rigorous enough that we can sort of resolve that singularity at the center of the black hole on the side of the quantum computer description?
The answer is no, or no in the following sense, in the sense that I, Pedro, don't know. But so let me say a few words about that. So when we say that two things are equivalent to each other, that is useless unless you give me a dictionary, right? When we say two languages are basically equivalent, okay, that's good to know, but it's only useful if you tell me how to translate from one to the other. If I tell you, you can use fluids as molecules or with fluid equations, fine, but you want to have a way to compare both. You want to say, when I measure the temperature of the fluid or the energy of the fluid or the velocity of the fluid, in both descriptions, how should I do to see if I agree? And the same thing with this hologram picture. If I want to describe what happens in the center of the black hole, in the singularity of the black hole, okay, that's one question. What should I do in the quantum computer to answer that question, right? I better have a dictionary. I better have to say, if I want to know about A, what should I do in the quantum computer, right? If I want to know about the black hole, what should I do? And so in this research, in this holographic dualities, there are always many steps. And one step is establishing the dictionary. Because you see, when you say there's no space, it's all an illusion. And that's tough because, I mean, we do feel space. It's not like I feel like I am in space. It's not, you cannot just tell me you are an illusion and hope that I will go to sleep and everything will be okay. I'll be desperate, right? I need to have some notion that I kind of exist and I'm more or less real and I feel I exist. And so there should be a way, for example, of seeing that things that are nearby in space interact easily with each other and things that are far away don't. Where do I see that in the quantum computer? Is it like in the quantum computer, some information is in some bits of the quantum computer and some other information in some faraway bits, and that's how they are far away also in space-time? What does it mean to enter a black hole? Is it that some bits in the quantum computer are harder to access than others? What exactly is it? And it's hard. Some questions are easy to answer. For example, if you ask, what are the possible how do particles propagate in the presence of the black hole outside the black hole? That's relatively easy. When you start asking what happens when I enter the black hole, that's harder. What happens when I reach the center of the black hole? That's even harder. And so, do we have a complete translation of everything? No. But that's what makes it exciting. That's actually trying to understand what would be the dictionary for those type of black hole related tough questions is what I want to do in the next few years. It's exactly trying to pinpoint whether I will be able to compute it easily, like you said, or whether I will have to put it on a computer to try to run simulations and try to get some intuition. I don't know. Whether I will fail completely, I also don't know. But I think we cannot just say I have a dictionary. I should say I have a dictionary and I want to answer what happens when I reach the center of the black hole. Do I get destroyed, or is the singularity resolved? Is there really a singularity, or is there some portal to another space-time or some crazy whatever? Or even wilder things that people have conjectured in the past. What happens when I enter the black hole? Normally, we learn in school that nothing happens, that it's very smooth. You enter the black hole, you don't even know you are entering the black hole. Only later did you realize, oh, oops, I entered the black hole. Now I cannot get out. But a priori, you would say nothing should happen. But then there are theories that there are people that say, no, there is some kind of firewall in the surface of the black hole and you cannot enter the black hole and so on. So that should not be a matter of opinion. You should not have opinions about these kind of things. It's physics. You should compute and say, what's the answer? And so translating these fundamental questions about black holes that are really the dream arena for thought experiments, where people have lots of opinions into, if you want, boring questions about problem solving, about trying to solve some mathematical problem. Like I said in the beginning, that's the kind of thing that motivates me a lot. Is one thing that I want to push in the next few years, is trying to make these questions about black holes more rigorous from this hologram point of view.
If we jump back to your description of your messy room where you're throwing clutter into the room and eventually you form a black hole.
Yeah.
Let's say, and you also had this other picture of a glass that you break, right? It has more entropy. after it's broken as compared to before it gets broken.
Yeah.
Let's say I form a black hole from glasses that are not shattered, and then I take the same amount of mass of shattered glasses and I throw them into a black hole. Right. In one situation, I start with very low entropy matter, and the other situation, I start with very high entropy matter, and I form black holes. Is there a difference between the two black holes at the end of the day?
No, that's a beautiful thing about black holes. We say that black holes have no hair, and it's really like they are really this bald object. A black hole, you look in sky. How do you see it's a black hole? It's because you don't see it. You see really a black circle. Right, and why is it black? It's black because light cannot get out of the black hole. And so if light doesn't leave the black hole, it doesn't hit our eyes, and therefore we see a black thing. So black holes are black, and if I look at a black hole and I tell you how much stuff is inside the black hole, and how much is that black hole rotating, that's basically enough to tell you everything you can know about a black hole. So black holes are, at the same time, the messiest objects inside, but at the same time, the cleanest objects outside, if you want, right? That they are described, you just say, here is a black hole, and it has 5 solar masses. That's it. That's the description of this object. And yet, inside, it is as messy as it could be. Now, this notion of building the black hole from shattered or not shattered glass, it makes sense when you are carrying the glass very far away and there's almost no gravity, right? But then eventually, when they are all inside the black hole in this huge gravitational force, everything is shattered. You're not going to keep the glasses intact for long.
I see. So it's through formation. The hypothesis is that the black hole either orders everything in the same way or disorders everything in the same way. So there's really, at the end of the day, you always end up with the same sort of object.
Seen from the outside. From the inside, we don't know. If you ask me, when I jump inside the black hole, is it also exactly the same? What is inside the black hole? That we don't know. Right? We don't know. We think that the answer is that or most people would say it's universal. Most people would say, outside the black hole, it's all the same. That I think 99.9% of physicists agree. Then you'd say, as I enter the black hole, it's still the same. I would say maybe 99% agree. Then as the closest you get to the singularity, people start disagreeing. People start saying, well, the singularity probably knows about the stuff that formed the black hole. And some people would say a bit before the singularity would start finding differences between different black holes. You see, it's a bit like when you are describing hot milk. Hot milk, you have 2 glasses of hot milk. They are very different quantum states, but they taste the same. It looks the same. I mean, it's very hard to tell them apart. So you could have very different, you could have 2 glasses of, you could have a different glass of milk every day, and quantum mechanically, they might be very different. But in practice, often, when you reach a big number of particles, things tend to become similar again. And then the only thing that matters is what's the temperature of the milk, what's the amount of milk, and the percentage of fat. You have a few numbers, but you don't care about the gazillion million details that describe the quantum state of the milk. So the black hole could be the same. You have so many particles, it behaves effectively like a glass of milk or a piece of coal.
And the parameters there are the mass, the angular momentum.
The mass and the angular momentum,
So you said in 97, Maldacena came up with this toy universe where he has this correspondence. So there's the quantum, we can think of it as some quantum computer, then there's the hologram, which is the universe. This is the ADS-CFT correspondence, right? It's for people who want the terminology. So the question I have is, it's kind of, I'll have to remind you of the 2 parts. Why is it difficult to do this sort of correspondence in the real world where we really live, right? And then the following question for that, and I'll remind you if you forget, is if we're the hologram, where is the computer? Right? Where's this boundary where this hologram is sort of constructed at?
we have a crazy idea, which is perhaps we are an hologram. And then we have toy examples where that crazy idea is mathematically realized. Now, these toy examples are not perfect in many ways. One of the ways is the way you said, that it doesn't describe a universe with the geometry of our own universe. There are many aspects that make these toy models toys. They are, as I said, for example, I told you that this theory is a theory similar to our world in the sense that it has fermions and it has bosons and so on. But it has much more symmetry than our world. It has symmetry that rotate these bosons and fermions into each other. It's called supersymmetry. Our world doesn't have supersymmetry. Now, you have other examples of ADS-CFT, of theories without supersymmetry that just involve a few scalar fields. You mentioned scalars at some point before. But those are two simple theories. And the gravity dual, the dual of these quantum computers are theories that the gravity looks very different from the gravity in our world. So we know how to do different toys. Some toys have lots of symmetry. Some toys have less symmetry, but then gravity, it's not exactly the gravity we have, namely our gravity as gravitons and this other gravity as gravitons and many other particles coming for the right. And so we don't have a theory that is, if you want, realistic. We have different theories, and each of them has some aspects that are realistic, but others that are not realistic. But all these examples of ADS-CFT dualities, CFT is the quantum computer. The name is CFT, is conformal field theory. It's a particular type of quantum field theory. And ADS is anti-de Sitter, is one type of space-time where you can have all your quantum gravity effects like black holes and so on. And what type of space-time is it? It's a beautiful space-time that is a box, basically. So at some point before we were discussing spheres, and I was saying, oh, a sphere is something amazing, that all points in the sphere are the same, right? I mean, you have a ball and there's no special point. I mean, all of them are the same, right? If it's a beautiful sphere, you rotate, you cannot tell where is the North Pole. I mean, there's no North Pole, you just rotate and all points are the same. This is the same, ADS is the same. In fact, mathematically, the equation that describes ADS and the equation that describes the sphere is roughly the same. There are a few signs that change in the equation, but it's roughly the same. But it's not a sphere, it's a box. A box, what is a box? How do you know you are inside the box? You know you are inside the box if everything is dark. It's because you throw a ball to the wall and it comes back to you, right? So then you know, oh, I'm in a box. Right? You throw stuff and it comes back to you. Now imagine this universe where you wake up, it's all dark, and someone tells you, you are in a box. And you want to test this idea. So you take a ball and you throw it away. And then you wait, and the ball comes back to you. Oh, indeed, it looks like I'm in a box. And you do it in all directions. And no matter what direction you throw the ball, it comes back to you in the same amount of time. Then you say, oh, nice. It's kind of a very symmetric box, like a sphere, and I'm right at the center of the box because I throw the ball in the dark in all directions and it comes back to me in the same time. And now here comes the shocking thing. That happens to everyone inside that box. There is no special point inside that box. Everyone is in the center of the box. So you throw the box and it comes back 1 hour later. Someone else that you saw passing through you, some astronaut is throwing their own ball and it's coming back to him or her 1 hour later. Everyone thinks he or she is in the center of the box. So it's really the most symmetric box you can imagine. It's a box where everyone is in the center of the box. Now, as you say, we don't live in a box. At least not that we know. We think that we go on and the universe goes on forever. It's not like I'm going to hit a wall or that I'm going to bounce back and come back. So I have this theory where if I was inside the box, I could describe things with an hologram, but I'm not inside the box. So should I be worried? And the answer is we don't know. On the one hand, we could say, well, if the box is very big, who cares if it's a box or not, right? I mean, imagine I put a box that is million light years away from here. And if the universe was inside this huge box, I conclude something. The universe is not. Will the conclusion be wrong? It's hard to believe. Normally boxes in physics, we often introduce them as a trick But if the box is big enough, we don't care, right? We send the box to infinity, and we just say, I put the system inside the box to control my computations. But then eventually I send the box to infinity, and whatever I get there, I would say the hologram is there. So it will be at infinity. That's one answer that says, yes, it's true, the universe is not a box, but we could imagine it is, and imagine the hologram is very far away, and why would there be a big difference? The counter argument that some people could say is, that would be okay if it were not for these massless particles, because as we said, massless particles, they propagate very long distances. So can we really say that infinity is really very far away? Because if these massless particles, they are very good at propagating, right? I mean, recently we observed these black hole collisions that collided like 13 billion years, or no, not 13, like 3 billion years ago, right? So there were some black holes, and these waves of gravity were propagating for 3 billion years, and we measured them in 2016. So they propagated a very, very long distance. So they could really tell very big distances. So is it really fair to say, as long as it's very big, who cares if it's a box or not? So that's the situation we are in. Mathematically, boxes are easier to describe. It's easier. You just say, my system is between minus a and a in all directions. I kind of control the mathematics better. It's easier. And then I say, and then I send the size of the box to infinity, and I cross my fingers and I hope it's all good. The other approach would be, no, I don't want that. I want a new type of hologram that really starts from infinite flat space, not a box. Then you have to rethink things. Some people try to do it. There are a subset of people in high energy physics, in theoretical physics, that are trying to do this, to try to understand, could there be an holography directly for flat space, instead of starting with this big box and making the box bigger and bigger. I suspect these people will end up agreeing that the box being very big is the same as no box at all. But it's not a theorem. I'm not sure. I'm open-minded. It just turns out that it's the best we can do rigorously.
But the universe wasn't always big, right? If you
okay.
Right. So what does this picture look like if you go back 13 billion years when we were just a primordial soup? Well, the universe was.
Yes. That's the toughest question. That is the one. That's the hardest question, is when we do cosmology and quantum mechanics at the same time. I mean, black holes is hard, but you just touched on one point that is one level up. And that's very, very tough. We just don't know. There, definitely, we cannot say we are in a huge box. No, at the Big Bang, we are not. That's very tough. I don't know. Some people hope that the singularity of the black hole and the singularity at the beginning of the universe might have some resemblances. And the singularity at the black hole, that one we have some hope of describing with these holograms. We still don't know. You asked, how do I, in the quantum computer, how do I simulate what happens when I approach a singularity? And I said, that we don't know yet. We know how to ask simpler questions on the quantum computer. Those very complicated questions, we don't know yet. And it's something that I hope in 5-10 years we will know, but now we don't. And we don't know what will happen when we will answer this question. Maybe the answer will be so illuminating that we will say, oh, mathematically, this singularity and the singularity at the beginning of the universe, it's mathematically similar. And indeed, the equations are very similar. You replace a few signs, like I said before, and you change some times and spaces, and they look similar. Maybe the solution to what happens at that singularity of black holes is so inspiring, so interesting, so new, and that perhaps it will give us some aha moment that will tell us something about the singularity, or maybe not. Maybe we'll still need a key idea. It's possible that we need a brilliant idea for understanding the beginning of the universe that we don't have yet. And it's not obvious that holograms will help in that.
Let's switch gears a little bit and talk about another topic that you play around with. So the bootstrap is an area of physics that I've just never really read about it. I've never touched on it. It's something that I'm very much. It's a black box for me. So what is the bootstrap? And does it relate directly to these holographic dualities? How does it relate to quantum gravity? Why are you interested in it? That's a lot of questions altogether. So let's just start with, what is the bootstrap?
Yeah, the bootstrap, roughly speaking, is just trying to be smart to get to the result without too much work. So it's possible sometimes to avoid doing some computation. So in physics, there is a canonical way, which is of computing things, which is, what are the rules. I'm studying, say, some fluid, and I have some fluid equation, and I have to solve those equations. Given the initial position and velocity of the fluid, I study the final position and velocity of the fluid. That's the rules of the game. And now let's play the game. You pick a cup of coffee, some paper, and a computer, and you try to solve that game. So that's one way of doing it. You are given the rules, you play the game. There is another way, which is to try to see, suppose I want to compute some result of some experiment. Like we were saying in some quantum mechanics, the probability of the particle going to position A or the probability of going to position B. And I don't want to do the computation. And I don't want either because I'm lazy or because I don't know how to. Because sometimes the particle goes to point A and to point B through so many possibilities, interacting with so many particles, that the math is just too complicated. It's not just that I'm lazy. It's that sometimes if the quantum effects are very strong, it's very hard to compute. So what do I do in that case when things are too hard? There is the idea of, let's try to guess the result, if you will. Let's try to say, well, what's the probability of going to A? And you could say, well, it's a number between 0 and 1 because it's a probability. And you say, okay, that's not very informative, right? Like if you are an experimentalist, you will look at me and say, are you joking? But then you start saying, well, but that probability to going to A plus the probability of going to B, that's a number between 0 and 1 because it either goes to A or it goes to B. So if the probability, it cannot be, maybe both are 1/2, but both cannot be 2/3. They would add up to something more than 1. Okay, so now at least it's not totally trivial. Now you start saying, oh, the final outcomes of experiments, they have different probabilities, but they must start adding up to 1. They cannot add up to more than 1, this probability. And then you start thinking, oh, wait, but these two experiments that the probabilities add up to 1, actually, they could be related by some symmetry. Maybe there is some symmetry. Maybe, for example, they are basically the same process, swapping space and time, for example. And now you start mixing quantum mechanics with relativity. And then you start saying, oh, not only the probabilities are smaller than 1 when added up, but they are also related to each other because these two different physical experiments are related by some symmetry. And you start trying to, without doing the computation, injecting more and more things, more priors to what you think the result should be. And then, typically, the next step is using computers. You scan over all possible set of numbers that obey all those possible conditions. And you, in this way, you carve out the space of possible outcomes of experiment. And if you have enough constraints, maybe that space of what's possible and what's impossible, maybe what's possible are small islands. And if that is the case, that's good enough. You might not know exactly what's the outcome of the experiment, but if I tell you, well, the probability is between 0.72 and 0.73, oh, that's already very good, right? Then you know it. There's 72 to 73% chance of that happening. That's great without doing a computation. And then you inject some more information and maybe you shrink that island further to 72.5 to 72.6. And that idea of just by the power of thought and by the power of imposing more and more physical conditions, shrinking the space of possible outcomes and trying to guess the outcomes without doing a computation is normally what goes by the name of bootstrap. So the physical picture of bootstrap is that of you got a result that it almost looked like you should not be able to get it. It's like the picture of you lift yourself from your bootstraps. You push yourself from the bootstraps and now you are floating. That looks like impossible. And that's a little bit the impression that we have sometimes when we do these bootstrap computations. We start saying the probability is smaller than 1. So, duh. And then this is related by symmetry, duh. And each one by itself looks kind of boring and trivial. But all the statements together, miraculously, they tell you, well, if all that is true, then the outcome of this experiment is actually not that wide. It's a very small corner. And then you start studying spaces of possibilities, what's possible and what's impossible. So you see, it's exactly the opposite of these toy models and holography in that sense. In the sense that when you have a toy model, you have a very precise toy. You say, this is the toy theory of the quantum computer. It's supposed to be equal to this toy theory of quantum gravity. And let's study this toy theory in complete detail to learn about quantum gravity. Let's try to really study it in detail, in excruciating detail, to really learn about what could be the interesting features of quantum gravity. Right? It's like trying to understand human psychology by really focusing on one person in really full detail and understanding all its traumas and desires and so on. Really one person only. The other idea is the opposite. You are agnostic about the theory and you say, I want to study all theories at once. It's like a meta theory kind of question. You ask, I want to zoom out and I don't commit to anything. I want to study the possible space of personalities, right? The possible space of theories. It's the opposite approach to understanding human nature by trying to look at zooming out and saying, oh, maybe people go from happy to nervous. And you cannot be as precise. You cannot ask as sharp questions as you can when you have a precise theory. But the trade-off is that you have a much bigger, broader picture, and you are studying many more things at the same time. And so, now this is all very vague. Concretely, there are different types of bootstrap. We use bootstrap in the sense that I said when we study some scattering experiments, for example. And we would say, I want to study the probability of scattering experiments. And then, like we said, this bashing of particles that is very important in quantum field theory. And this bashing of particles, we don't know what's the probability of these two electrons colliding and producing these two electrons, but we know that if I sum over all possibilities, these probabilities are smaller than 1. And I start trying to constrain. And eventually I could tell people at accelerators at CERN, look, if you scatter electrons like this and you study this angle, you will likely get this probability. Let's see if it works, if it's in this window or not. And that's one type of bootstrap. And there are other types of bootstrap when you try to apply these ideas to other aspects of physics. You could have conformal bootstrap when you apply it to these theories that describe these quantum computers. You could have integrable bootstrap when you use it to study exactly solvable models in 2 dimensions, which is something that I also work on. And you could have different types of bootstrap. But in short, bootstrap is just, instead of doing a computation, you try to think cleverly to guess the result. And sometimes you can do it. I
have a million questions on this angle, though. So the picture I now have is that, okay, maybe you want to calculate some scattering probability of 2 gravitons, let's say, or something like this. But
yes,
usually you'd need a quantum theory of gravity to do the calculation. You don't have the quantum theory of gravity. And so you use these principles of nature that you hold to be true. I guess I can ask you what those are, and that sort of cuts out or gives you an approximate answer, even though you couldn't do the calculation. So that's the picture I have.
That's precisely correct, and indeed it was one thing we sort of did, and I will qualify it. Why I will say what without qualifiers, and then I'll qualify it at the end. I'll precise it at the end. Was precisely what you said. We said, I want to study scattering of gravitons, and I don't have a theory of quantum gravity. But what do I know? I know that at very low energies, I know how gravitons scatter. I know if I'm at very, very low energies, which is the same as saying at very large distances, I know how gravitons scatter. It's the same as how I know how the Earth and the Moon interact. The Earth and the Moon, they just throw one graviton at each other. And it's by throwing the graviton at each other that I know the force between the Earth and the Moon. So gravitons is the same. If two gravitons are flying apart, if they are very far away, they throw one graviton at each other, and that's how they interact. Right? Now, if they are at higher energies, namely if they are colliding head-on, then they are not just exchanging one graviton. They are exploding, they are exchanging millions of gravitons, then things become very complicated. But at large distances, when they are flying apart, they just exchange gravitons and deflect a little bit. And so, if you want, that low energy result for the scattering of gravitons is what we call the result given by Einstein gravity. That's the low energy result, which is well understood. Then what do we know? We know that as I crank up the energy, or if you want, as I scatter at smaller and smaller distances, that result must be wrong. And eventually it needs to be modified. Okay? It's a bit like, for example, the interaction between electrons. The further they are, the smaller is the interaction, right? The Coulomb potential, the force between the electrons, decays with 1 over the separation square. So if you separate them twice, the force is 4 times smaller. You separate them 3 times, it's 9 times smaller. But the opposite says that if instead of separating, if I bring them closer, 1 over the distance, if the distance is very small, that's huge, right? 1 over 0 to some power is infinity. So as things get smaller and smaller and smaller, now this becomes very big. So what does it mean? Does it mean that there is some infinity and the electrons don't exist and the universe? No, of course not. It just means that as we bring the electrons closer, now electromagnetism needs to be corrected and other effects are also important. And if I bring them a little bit closer, I start seeing the first deviation from electromagnetism, the first deviation from the Coulomb force. And the same thing with gravity. If I start scattering the gravitons, first I see usual scattering, and then as they become closer, I start seeing the first correction to gravity. That first correction will tell me something, not much, but it will tell me something about the theory of quantum gravity. Different theories of quantum gravity would give different corrections to the force, to the Newton force, if you want. The analog of the Coulomb potential is the Newton force of attraction between bodies. And so you have Newton's force, and then as things become closer and closer and closer, it gets a little bit corrected, and that first correction would be the first correction to gravity, is the first effect of quantizing gravity, if you want. If we are experimentalists, we measure the force of gravity, right? Very well. Can I imagine measuring the first deviation from it and start learning about the theory of quantum gravity? And now, can I, based on this bootstrap idea, start putting bounds on what should that correction be? So that's one thing that, since we don't have a theory of quantum gravity, we could say, so let me try to put this possible scattering of gravitons in this thought experiment, ask that it obeys these sacred principles, which are quantum mechanics and relativity, basically, and ask, can I then predict the magnitude or the size of the first correction to Einstein relativity? And then people could go and measure that, and depending on what that correction is, it could give us some hints about what the theory of quantum gravity really is. So that's something that we were working on. You were going to ask me something, but then I want to qualify a little bit that what we did is not as fantastic as what I just said. Otherwise, I would be overselling and I would feel bad.
So the question that I have is, so you mentioned that, sort of offhand, you mentioned that you could apply this same procedure in regimes where we really can do the experiment. So you can go away to CERN or somewhere and say, if you do a scattering of 2 electrons using the bootstrap, this is the sort of result you're going to get. If we go and use the bootstrap in regimes where we can do the tests, do we get the right answers, or does it does the program work where we can test it?
Yeah, it works where we can test it. Let me say it like this. There are 2 extreme behaviors of particles, which are, they are almost free and almost nothing happens, or the opposite. A lot is happening and they are interacting a lot. When almost nothing is happening, you could ask, does the bootstrap work in that case? And the answer is yes, but who cares? Because if not much is happening, you can also use normal computational tools and you would get the right result. So when things are easy, finding a new way of doing easy stuff, it's not the most exciting thing. It's fun, it's good, it's important for self-consistency, but that's not what's exciting. What's exciting is when you have regimes where the other methods don't work, when particles interact a lot, when it's at higher energies. So, or in between, when it's not really super hard, it's not super easy, but it's intermediate. And there you could kind of study a little bit with traditional methods, a little bit with bootstrap, and see whether they could give some interesting feedback. So there are a few areas of physics, for example, studying scattering of pions. Pions are very light particles in nature that we cannot do with tradition. We have hard time doing with traditional so-called perturbative methods that the bootstrap gives some results that are comparable, that are compatible with experiment, but better than traditional methods. There are other examples of physical theory. So the three ones that I like the most is pions, the study of the dynamics of flux tubes, and gravity. And those three examples, I think, are three beautiful examples where this bootstrap tells us something that other methods struggle to do.
Do you mind if I just jump in and ask you a question here? So you mentioned flux tubes, and this makes me think string theory. So you're able to use these truths of nature that we hold to be, you mentioned quantum mechanics and relativity, and I've done a little bit of reading of your paper. So there are, to put out some other names, is crossing symmetries, unitarity, analyticity, and things like. So there are these principles that you take axiomatically and say, what does the space of possible theories look like? Mm-hmm. Does string theory pass the test? So string theory is our best theory of quantum gravity, let's say. Does it sit within the space carved out by the bootstrap?
So that, let me say that was, if you want, one of the main motivations for us to ask what could be the corrections to gravity. So we want to know how the universe works, and we don't know how it works. And as you said, string theory is one possible idea for how the universe could work at these very, very high energies, where quantum mechanics and relativity are important at the same time. So it's one so-called theory of everything. It's one theory that would correct gravity. If string theory is the theory of nature, then the corrections to this Newton force will have a certain pattern that will be the pattern given by string theory. Then the question is, when we study, on the other hand, the bootstrap, we get some allowed values for these corrections. How do they compare with the values that string theory produces? What we found for us was very surprising. We found that the values that this very agnostic bootstrap idea, which is the idea I don't commit to any theory, I just ask what values can I take, they gave me some allowed values for this first deviation to gravity in some units that was something like 0.29 to infinity. Namely, it's not, you could say, oh, it's not like saying much, but it could be something. It could be 0.129, 0.2, 0.3, up all the way to infinity. But it could not be minus 0.5, for example. It could be some big range, but starting around 0.129 or 0.13. And it turns out that the values that string theory predicts are exactly 0.13 to infinity. Now, it could be a coincidence, or there could be many explanations. If I wanted to oversell the result, I would say, oh, this looks like evidence for string theory being the only possible theory that completes gravity. Mm-hmm. This would not be honest. It would be disingenuous. Because perhaps there are many theories of quantum gravity, but they all produce numbers that are between 0.13 and infinity. the fact that string theory produces that range of numbers, I don't know if other theories also produce that range of numbers. What I know is that if some theory tells me that the correction to gravity is something like 0.005, I know that theory is wrong. Or I know that it violates some very sacred principles. So if that theory is right, it means that something that we thought was very sacred, like quantum mechanics, must be wrong, which is much more serious. Why do I say that we must be careful interpreting this result? Because one, it's just one number. It's the first correction. It could be a coincidence. It could be that all theories have that range of number. It could be that that number agrees very well with string theory, but the next number gives some range that is much bigger than string theory, and now I don't no longer think that string theory is special. And moreover, and that's very important, this study that we did was done in the context of these so-called toy theories. Namely, it was done asking, what is the possible space of theories that have this big symmetry, this big supersymmetry that I said before that relates bosons and fermions? That's not a symmetry of the real world as far as we know it. It's a symmetry that makes the computations easier, and that allowed me to do this computation and study it. We could do the computations with less symmetry, yes, but it would take much longer running the computer. We didn't have the energy to do it yet. And moreover, if we did, we would get some range of values that we would not know what to compare with, because it would be harder to compute in the computers. And then I would get some range of values. Imagine I get, say, I don't know, from 0.4 to infinity. But then with less symmetry, I don't know how to study string theory with less symmetry. So I don't know what string theory would give me, and I would not know what to compare with. It would still be a very interesting computation to do. I think we should do it. I think we will do it. But I want to develop the numerical methods a bit more before we try to attack that problem. But this is a direction that I think it's cute. It's about asking what is the space of theories? And then you look at the space of theories. In this case, it was just a number. So the space is just what values are allowed in a line. So it's not the most exciting thing. But if you have various numbers, it would be like a sculpture. Or if you have, say, two numbers, it's like a map of blue and red regions, right? Blue is allowed, red is forbidden, and you could have some beautiful maps. You could have peninsulas, you could have islands, you could have big continents. It would be very rich. So as soon as you start putting more parameters, you have this space of what's possible and impossible. And then it opens us to the idea that we could try to explore spatial real estate in this map. We could ask, oh, there is an island here. What is the theory that lives in this island? Oh, there is a peninsula with a sharp tip. Is there a nice theory that lives at the tip of the peninsula? And so then we could go and ask, when we get this picture of the space of theories, we could ask, are there special theories? Could it be that, like this mark, you are here, right, in the map, is it at a special location or is it in a boring location? And there is reasons to expect that it might be in a special location, because typically we go to special location. We go typically to the boundary of what's possible and impossible, right? People live in the coast. Why do they live in the coast? They like living close to water. Or if you are in Canada, like I am, people live in the coast between Canada and the US because they were trying to go as warm as possible and they got stuck wherever they could not go anymore, right? And so often in physics, there is this idea that you want to maximize something, proximity to the water or temperature or something. And the fact that you are trying to minimize something pushes you close to boundaries, right? Because you go as far as you can go. Then you hit a wall, you cannot go anymore, right? And so perhaps special theories are at the boundary of what's possible and impossible. So this could be a strategy for looking for exciting possible UV completions of gravity, quantizations of gravity, or special theories that describe quantum behaviors that we don't know how to describe.
So there's
but
this...
it's too... Yes.
You paint this picture that there's this space of theories and the theory of everything, whatever it is, this theory of quantum gravity, your guess would be that it lives right at the boundary of the impossible in some sense.
That's right. I would imagine that it should live at the boundary between what's possible and impossible. More than at the boundary. If I were to guess, I would imagine it's at some kind of tip of some peninsula. Yes, that's really the best place to be. It's really, you have water from all possible sides.
Another topic, because I want to wrap up the conversation, because this is sort of like on a high note. I like this idea of living at the boundary of the impossible. You interact with a lot of physicists, right? A lot of great physicists at the Perimeter Institute, and also you travel to South America occasionally, right, to work as well.
Yes. I share my time between Brazil and Canada. Yeah.
What makes someone a good physicist? Right? Who do you like working with? What are the sort of people that you really benefit from interacting with?
I think for me, the most fun aspect of research is this idea of touching upon something that is true that you did not know before. It's a little bit like there is this Platonic world of true things. You are trying to look for it and it's cloudy. And sometimes you manage to kind of open a portal to it and you see something, oh my God, it's amazing, this is beautiful, and you push it down, this truth. And then you push it down and you put it on the blackboard and you discuss with 2 or 3 people. And that process, when you get this truth that is still fresh and that you understand something, that's why it was always bouncing back with the same velocity. The velocity was the same. That was because that idea that you got this fresh truth and you finally share it with our colleagues and with a small group of people, and you are trying not only to enjoy it, but try to see what it is trying to tell you and how it is trying to give you a global picture of what's going on. For me, it's the most fascinating thing. So people that I love working with are typically people that I like discussing in the blackboard with. So that process of, so there are some people that are brilliant, but that are more computationally driven, that like to sit alone in the computer, or people that have a style of research that is just too fast and jumping too quickly between topics without calm to appreciate the beauty of something that we just discovered. Those I would struggle a bit more to work with. So I don't have a strict preference. I end up working mostly with students and postdocs, so that's more my style. I like it. It's something I tend to converge more towards, but I'm open-minded. I work with everyone. I don't think there is someone. But my style, I think, in the spectrum of very rigorous and very speculative, I'm very mathematical. So I tend to do things very, very rigorously. Within the people that do things very rigorously, I try to be as speculative as I can. But so I'm in that quadrant, very mathematical, trying to be speculative as well, but definitely from a more rigorous point of view. So I tend to interact more with people that are very mathematically minded as well, and that.
Is there a discovery that you've had or something that you've uncovered that you're most proud of?
No, what I'm going to say is not out of being humble, but it's really true that in the kind of research that I do, things are really done in groups of 2 or 3. So I don't think there was ever something that I really truly associate to me. There was a period before coming to Perimeter where we understood very well the energies of these holograms that we were talking before. That was basically the reason why I was hired. It was, we have this duality between the hologram and not the hologram, and we say things are the same, then we better compute something and see that it works. And we did it. We did that computation. We studied the energies of the hologram in the quantum computer and the energies of the quantum gravity, and we saw, oh, they are the same. And many people were trying. It was an open problem. It was like a race that every year we would make some progress, and people were trying. And in 2009, together with 2 friends of mine, we kind of managed to solve that problem. It was not me. It was we did it together with them. That result, I think, is super cute. There were some ideas. I don't want to go in this direction. I would rather describe the physics than.
Then can I ask you about the
I'm
physics?
yeah.
Can I ask you about this? So this is something that I'd like to understand better. This correspondence between the hologram, let's say, and the quantum computer. So this duality. So what you're saying is this work that you completed, you had the gravity side, and you calculated some spectrum of the theory, and then you calculated the spectrum on the other side, the quantum computer side, and you lined them up, and they sort of overlapped. And so then you could show this was a rigorous connection between the two sides of the duality. So it's through this process that you make the duality rigorous. Is that the case? Because I'd never understood how you get this duality, how you actually work out that they correspond to each other.
That's precisely true. So I think you said it correctly. So I don't think I need to add much. But that's exactly what we did. So we said, let's in the quantum computer, it's a physical system. What's the simplest thing we can study in this physical system that we often do when we study chemistry is what's the spectrum? What are the energy levels, right? That's what we use it. When we look at a star, we see what's the spectrum of the star to tell what it is made of, right? So we look at a star and we see the lines and we say, oh, there's lots of hydrogen and a bunch of other stuff and so on. So the energy levels of something is the most basic thing you can ask about a physical system. What energies does it have? And when you have these quantum computers, these energies, they should do something rather cute. First of all, this quantum computer should have a knob. Why should it have a knob? Because this quantum computer is put at the boundary of this box, and the box could have any size. So there should be a parameter that I change that changes the size of the computer. That makes it from a very big computer to a very small computer. It should have a knob. It should have a parameter. Then when the parameter becomes very big, this box becomes huge and things become as if there was no box, like we were saying. Or at least that's what we hope, and that's what we see in the examples we can compute. And then it should be just what are the energies when, forget about the box is very big, so there's no box, you are just looking at empty space. What could be the energies there? And like we said, particles, there are two possibilities. Either they are heavy or they are light. So the energy should be zero if it's a graviton, because the graviton has zero mass. Or otherwise, there should be empty space, and then the electrons and so on, the massive stuff. So there should be this gap. There should be an interval between zero, where the gravitons and everything that's massless is, and then stuff. And then there should be lots of stuff. And so we have to see this. We have to see that the spectrum, when I change this parameter, some stuff remains zero, and then the other stuff goes up and forms a gap. And not only it should form a gap, but the gap should be precise. Because what's the first state there, the first massive state? It's the first string theory, the first string that is vibrating, the first massive string mode. What's the second level? It's the second string mode that's vibrating. And so not only we knew the gap, but we knew all the energies that we expect to find. It's all the possible vibrations of the strings that could be inside ADS. So that's what the energies in this quantum computer, they have to do. When the quantum computer becomes very big, they better have a gap. And after the gap, we better find the energies of strings. Even though the quantum computer has no strings, it is just a theory of particle physics, like we said. But suddenly, it should somehow, the energies should not only form a gap, but after the gap, there should be the energies of all possible strings of string theory. That was very non-trivial. It didn't have to work. And in 2009, we had a beautiful plot where we tuned this knob and we saw exactly this happening. And so that was very, very satisfying.
Your happiest day at the board?
That was not at the board. That was a very happy day, but it was...
that was computer. That was
that required a computer. That required a computer. Yeah, but it was quite fun. So we had to do this computation as we change this knob. So we had to do it when the knob is 0, when it's 0.1, when it's 0.2, when it's 0.3, when it's 0.4, 0.5, or many values, so that we could plot the curve. And so I was where was I? Yeah, I was visiting Porto and with my colleague, Kolya Agramov. So this was a project with me, Kolya Agramov, and Volodya Kazakov. And Kolya and I, we were in Porto, in the Porto University. It was during the summer. And we had pen drives. And we went to all the computers of Porto University. And in each computer, it was our manual cluster. We put a small script that would run a mathematical file computing the value of the energy at a given coupling, at a given value of this knob. And so we went from the basement, first floor, second floor, third floor. The third floor computers were the most powerful ones, and the basement ones were the weaker ones. And so in the basement, we had a computer running the spectrum in the easy regime of the field theory, when the coupling is small, when things almost don't interact, like I said. And then in the top floor, we had it running the value of the plot in the hardest point, when the box is very big and a lot of quantum stuff is going on. And then we had the guess for what it should be, because we knew, as I said, we had a guess that should be this gap, and then there should be this energy level. So we had a dotted line where we wanted these points to go. And whenever the computer would be running, and it would be solving these equations by a method known as iteration. Iteration means that you get a value, then you compute a bit more, you get a better value, then you put that better value, you get a better value, and you get a better value. And what's fun in an iteration is that you see the value changing. You see the value goes from 0.9, 0.8, 0.78, 0.777, and it starts moving. And so we had this dashed line, and all these computers were connected through the internet, and we had a script that would send the updates of the iterations, and we would see them live, the points moving from various directions. And over that night, the points all approach this dashed line that was what it should be if it was the energy of a string. So I remember I was home with my parents watching Dr. House. At the time, it was a popular TV show. And I had the computer on, and whenever a point would move, it would make ping, ping, ping. It's probably very annoying for them. And I would look and I'd go, oh my God, it's approaching the dashed line. And that was super amazing. When finally all the points landed beautifully on top of the dashed line, we were really happy. Yeah, so that was a very fun moment.
I'd usually want to end the podcast right there, but I have to ask you two more questions. If you could solve any physics problem, it comes from on high, you work out the answer tomorrow. What is the question that you're most curious about answering? What is that one thing that you would love to have the answer for?
So I think what happens at the beginning of the universe probably would be the question that I really don't have a clue. I would love. I don't know what to do. I cannot go to the blackboard, erase my blackboard that I have here, and do like Bart Simpson and write what's at the beginning of the universe many times. And I just don't know. I don't have any good idea for that. Now, maybe in 10 years, maybe in 15 years, maybe in 20 years, I'm approaching that. For example, I told you that I'm very much thinking about black holes these days. I was not 10 years ago. Black holes is news for me. I was not thinking about black holes until very recently. So I very much would like to understand some aspects of black holes from a somehow different point of view that people have studied in the past. And I hope that this novel perspective on black holes might prepare me so that in 10, 15 years, I'll go and try to study the beginning of space-time. And I would like to understand black holes more from this quantum computer point of view. I would really like to try to perhaps sacrificing realistic aspects of black holes. I'm not going to describe astrophysically relevant black holes with their accretion disks and all the realistic properties of black holes. I'm happy with describing toy models. I'm happy with approximate idealized solutions of black holes. But I want to have setups where questions about black holes are not questions about opinions, where I don't want to be able to, I don't want it to be about opinions, about what do you think happens when we pass an horizon of a black hole. I want, at least in those theories where the setup is well posed, I want the answer to be sharp, well posed, and mathematically rigorous. So for me, in the next few years, I would like to try to make some speculative questions about black holes boring, if you wish. try to make them sharp.
If you were a betting man, do you think that there is a final theory of everything, and do you think we'll find it?
I think there is probably a final theory of everything. I think the probability that we landed on it yet is small because there are so many possible theories. I don't have a particular attachment to a particular theory, but I think there is a lot to be gained by understanding toy theories. It's really a little bit like there is a lot to be gained by reading a romance if you want to learn about human nature. There is a lot to be gained if you learn about one person very well, you really learn about a lot about human nature. And while we might not know what is the ultimate theory of quantum gravity, if we understand one or two examples very well, this will be amazing. And we are at the point where we don't know what's the ultimate theory. We don't have enough energy. We don't have the capacity of going inside a black hole and checking very strong quantum gravity effects. But we have examples that are consistent mathematically. And at least in those examples, we better answer these questions. What's the singularity? What happens when we enter the black hole? And then we should struggle to find such toy models, not only to flat space, but more ambitiously to cosmology, which is really a key question. We need to find approximate models of cosmology where things are partially under control.
Pedro Vieira, thanks for coming on the podcast.
Oh, thanks, Shane. It was great fun.